Good morning. Welcome to the EasyPower Refresher webinar series. My name is Jim Chastain. I'm with the applications group here at EasyPower, and today we're going to be talking about arc flash analysis for typical photovoltaic systems. As we usually start our discussions in a webinar, we use poll questions, and so I invite you to participate. Certainly there's no obligation, but it helps direct some of the conversation. And so today we're asking, how often do PV systems include batteries? And then how large are your projects? So if you would help us by indicating how this fits to you, and we'll just give this about 10 seconds to collect the feedback. Here's how people have voted so far. Good, thank you. Let's see the next one. And then how large are your projects? And I do expect this to kind of be all over the map, so I again appreciate the feedback. Here's how audience indicated things shape up. So let's kind of get into our discussion. So for those of you that have EasyPower tools, there's a complete chapter in the user's manual dedicated to DC modeling and analysis. And then there's some sample files that are already pre-drawn in the sample folder that are used for the discussion in the user's guide. So I encourage you to take advantage of those. And in part, I'm going to be addressing essentially a combination of both of those models as we're going through the next 30 minutes. The other topics I want to touch on as we kind of go through this discussion is essentially the components that are in the device library, and in particular the protective devices in the DC section. We're going to talk a little bit about the 2-second rule and when to use it. It's a sore point in the discussion of arc flash, at least for me. It turns out in the DC systems, this is one of the areas where it's a most useful feature. We're also going to talk about the integrated method, which is a function in the EasyPower analysis that is basically custom, or I don't want to say proprietary, but it's a feature that's available only in the EasyPower tools. And then we're going to extend this discussion to include battery systems as we do that. Okay, for starters, NFPA 70E, the most current version, or the version that's soon to be in effect, is 2018. Informative Annex D5 is focused on direct current incident energy calculations, and this is up to 1,000 volts. And what's described there is referred to as the maximum power method. And basically, the assumption or the presumption that's used in this theory is that the maximum power is available when the arcing voltage is 1/2 of the system voltage, and that's essentially the rest of the system impedance is matching what the arc resistance or characteristics are. And so you'll see in the calculations how that's implemented. Everyone agrees that this is conservatively high, and there is a fair amount of work, I think, behind the scenes in developing an additional model. And so that's one of those things that you want to stay tuned for the changes as they happen. So again in D5.1 of NFPA 70E, arcing current is defined as 0.5 times the bolted fault current, and that's how they implement the 50% voltage. And then incident energy equals this equation, which is some percentage of the system voltage times the arcing current times the time of the arc, all divided by the distance squared. And you'll notice at the bottom of this discussion, there it says, for exposures where arc is in a box or enclosure, it would be prudent to consider additional PPE protection beyond the values shown. In the previous versions of NFPA, and the reason this is shaded gray is that the reference was an advice to use a 3x multiplier if it was in an enclosed box, and currently that's what's in effect in the EasyPower calculations. So when we start talking about the way EasyPower models a photovoltaic cell, these basic parameters are used as much for correlation between our reference points and what's pretty common knowledge in the semiconductor power industry, and that is the short circuit current is defined as the maximum current that the module or the system will produce, and it applies at every juncture in terms of cells, strings, or modules. The open circuit voltage is the maximum voltage that the device will produce. The peak power is actually the knee of the curve, if you will, and that's the maximum output that the device can provide. And then all this combined gives us the ability to come up with a power rating for the module. So the example file that's in the EasyPower installation under samples is called Photovoltaic.dez. And in essence, PV cells are combined to create a PV module. PV modules in series create a string, and then PV strings in parallel create an array. And the devices in series up the voltage for the modules for the ultimate string, and then the array total current will be all the string currents in parallel. So in the case of this particular example, we're assuming that we have a custom 40 kilowatt array using modules that have a short circuit current of 6.7 amps and an open circuit voltage of 66 volts. And so we're constructing a 10 by 10 custom array such that our short circuit current now is going to be 67 amps. The open circuit voltages will be 660 volts. And then the peak power will be at 600 volts, giving us a 40 kilowatt system. So let's jump into EasyPower and see how this looks. Now, as I mentioned, this is under the EasyPower sample module, sample folder. So when I go into Open File, Samples, I can find the photovoltaic example. And I've got mine write protected so I won't mess things up. And it looks like this. Now, one of the complaints, if you will, that we receive back from customers is that we take great pains to make it appear very easy to produce calculations from the tools. And I repeat often that the tools will not make you a power systems engineer, but it will make much easier for you to communicate with a power systems engineer. And to that end, there are a lot of features in this particular example that we have I glazed over, if you will, some of the details, thinking that power systems engineers will pretty much get it. And so I don't want to get too much down into the weeds, but there are a couple points I would like to make. First of all, this example was actually created before there were that many new devices, if you will, dedicated to PC DC circuits. And so the first thing I wanted to do in discussing this is go in and actually replace this fuse. We show this as a busman fuse. Well, if you look up the specs for the 170M series, they're really not dedicated to a PV system or a DC system. You have to compensate for it, which at the time we did. But what I'd rather do is utilize one of the PV series fuses from Busman. And in this case, we're going to stay with the 100 amp fuse because that's a relatively conservative approach. We're using a 67 amp module or an array, and we're going to fuse it at 100 amps, and given some conservative scaling and compensation, that's a rational thing to do. And now I'm going to take a copy of that and put it into my other sister branches, or if you will, branches on this side. And for now, I'm not going to replace all of them because at some point I want to compare the two fuses to kind of make a point. All right, so obviously that's relatively easy, but it brings up another point, and that is what if you have a device in your system or in your design that's not listed in the EasyPower device library? Well, one of our basic commitments to our customer base is if you come up with a new product, and frankly, manufacturers come to us every week with whole lists of new families of devices they like in the library, and we try to accommodate that as time permits, but frankly, we prioritize any customer coming to us with the request, hey, Jim, I want to, actually, the report doesn't come to me, the request comes into tech support. I have a fuse in my system. It's a Busman or a Square D or whoever it is that may be producing the fuse you're going to use. If it's not in the library, provide us with the data sheet, and we may have the commitment to our customer base to turn that request around and supply the model back to you to be able to use in your project within 48 hours. So that's part of the ability to, if you will, update your system as new devices are introduced into the market or into your projects. All right, I want to go into short circuit focus. So this is already pre-drawn. Oh, I did want to look at how I've constructed the array. So we already described this as a custom array. We know it's going to be 40 kilowatts. We know it has a short circuit current maximum of 67 amps, and the open circuit voltage is 660 volts, which gives us a peak power of 600 volts for the max power calculations. We're able to kind of cut and paste to make everything. Now, if you look at certain reference documents, there are different philosophies on where fuses need to be placed in the system. In this particular case, we're using an array. Some people would prefer to fuse strings. Others would prefer to fuse modules. And so the tool allows that for whatever size element you want to use here, and then the ability to kind of cut and paste as you expand out your diagram. So a lot of this may be different from what you would expect to do based upon the size of the system that you're designing. All right, let's go back into short circuit focus. Now, we mentioned earlier, or I didn't mention earlier, but the tool, as I draw my one-line diagram, I have the ability to have both AC equipment, which is going to be over here in my utility connection, and DC equipment in my one-line diagram. And to that end, I can actually also include devices that may not necessarily be standard components in the library, but I would document and I can implement those. And if you have needs to do so, I would suggest you contact tech support and say, hey, I'm trying to use this type of relay or this type of a system or this type of a scheme. How is the best way to incorporate that in EasyPower? Now, in terms of sizing the fuses, each of these fuses, if we have a fault in this particular area, is going to be seeing the contribution from all the other strings, all the other arrays. And as we go into short circuit focus and look at the current, fault the current, we see each of these arrays contribute 67 amps to a fault on this central bus. If we were to get a fault on one of the feeder systems, then it would see, as we have it set up, we can't really see what that fault would be. The best place to look would be down here. We see that the rest of the system would provide 460 amps, while this one array would provide 67 amps. Well, the problem is for a 100 amp fuse, this does not produce a clearing in a 460 amp fault does not necessarily trip that fuse in a very fast manner. So this brings us to the use of our short circuit options tab. And if we look at the arc flash hazards, we see that this example has excluding main, and it's already set up for 2-second max time limits on each of the voltage ranges. What this is for, what the purpose of this particular box or entry is rather than let the protective device limit the fault calculations, is to use the basic parameters that are part of the IEEE equation or the max power equation, but stop the calculations at a fixed time point. In this case, we've entered 2 seconds. There's an issue with that, in my mind, of prematurely jumping to that conclusion, because what we find if we fault a specific bus is that we're seeing artificially that calculation being limited without really knowing what the full extent of the energy release might be. Now, in the case of something that's this low voltage, 600 volts is not low voltage, this low a current, we're talking about a bolted fault current of 535 and an arcing current of 267 amps. That's relatively modest energy. The point being, the conventional calculation is usually using the first half cycle current. And so in EasyPower, there's the ability to use the integrated method, which allows us to use half cycle current for the first half cycle, 5 cycle current for the next 5 cycles, and then 30 cycle current or steady state for the balance of the time. Well, in DC, without any reactive components that are contributing over time, the DC component all stays the same. And so what we see is this 267 amps that's going to be continuous through the full 2 seconds at a steady state rate. Now, the point I want to make with all this is that the problem with using this short circuit voltage setting is this applies to a voltage range, not just certain components. And so if we have a 480 volt system over here or a 600 volt system, AC system, this limitation is applying to them as well. And I don't think that's necessarily a good idea if we haven't looked at the currents involved. So if we were to see a fault here, it also has a potential for being limited to 2 seconds. In this case, we have arcing current that's much higher, and consequently the trip times, the tripping units are working as they should, in this case the fuse. But my point is, by setting these global entries for 2 seconds, we artificially limit other parts of the system that we may not want to see limited. What I would suggest is not to limit the calculations on a global basis. Instead, go back and see what the actual currents are and the actual energies are. And we can see artificially when there's no limit on the DC bus, I double click just this combiner bus, we have a very high incident energy calculation. So clearly that's unrealistic, and clearly it needs to be limited by our calculations. Well, the way to do that without interfering, if you will, setting a global set point, in database edit, go into the data dialog box for that bus, and under arc flash hazards, use user defined times, and this is where I want to put my 2 seconds. Now, the advantage of doing it this way, and I also want it on my individual DC buses down here, is to go ahead and put this 2 second limit on each of these buses. And again, by setting one bus, copying, and then pasting to the other buses, now we can see that when we go back to short circuit focus, granted I've only got this bottom half changed, but you can see here when I fault this bus now, I still have my 2-second limit in effect, but I'm not going to be affecting any other part of the system. Okay, so what have we done? We've considered device libraries, the fact that there are some PV-related or PV-specific components in the system, so our examples may not be as up-to-date as we like them. We've talked about how you can add or have added to the device library any unique parts or new parts that you're going to be using in your system. We talked about the 2-second rule, how to apply it on a global basis, which is a short circuit option, and then how to apply it on a local basis for each bus. And we've talked about the integrated method. Again, it doesn't make that big of a difference in calculations, except that if we use momentary and apply it, we'll find that really nothing's going to change on a DC basis because that doesn't change the limit on the current. So where it comes into play is more on the extended faults on an AC current, or where we have loads that are going to decline over time. Okay, one other thing I wanted to touch on, and I'm going to add a battery bank to this example. And again, we have another example in the samples folder that has a DC link and a UPS battery backup system. So I've cut and pasted those batteries into an array over here. And this is where all of these rules start to have a greater import, because the fault currents are much higher in a battery system than you will see in individual arrays. And so as I go, well, let's talk about batteries are characterized essentially by the total rated voltage, the internal resistance, and then the rated current. And clearly, if we go into a fault mode where we're shorting the output of that battery, then there could be a very high release of current. And the limiting factor is going to be the internal resistance. So here you can see if this bus faults, we're seeing 6,000 amps come out of the battery. If this bus faults, we'll see a total of 17,000 amps because we have 3 batteries in parallel. And you can see if we isolate these other branches, we still have a 5,000 amp bus fault. So this presents the same kind of a problem in terms of calculations. So let's go into calculate the incident energy. Let's fault this bus. Now here again, we got much higher arcing current, and I've set my time at 200 seconds just to see how long this will be. Nothing changes over time if we look at the other time elements as far as 5 cycles, 20 cycles, or half cycle. So now we go back. Now when we have a decision to make on these 200 volt batteries, whether or not we make this a global setting. Well, in this case, we don't have any other systems below 200 volts. So I think, make the decision to apply the 2-second rule on a global basis. And before I get too anxious there, let me make sure I'm talking the right thing. So these are 600 volts. So I take that back. So we are going to do a global change at 600 volts. Short circuit, 600 volts. Apply it. Fault the bus. Arrange for arc flash. Now you can see, even if we limit the the calculations time to 2 seconds, we have 151 calories instant energy. And so these can be an excessively dangerous situation that we wouldn't want people working on these whatsoever. Down inside the battery compartment, it's going to be less, but still a dangerous situation. So these are real hazards, and I think thought must be given to how battery systems are modularized, isolated and fused, and then how people can be protected when they're working in a live system. All right, I think that kind of covers the issues that I wanted to talk about. There is a lot more detail, like I say, in that manual on chapter 20, talking about how to model inverters and, for that matter, rectifiers. And for the most part, they are not going to generate at least arcing current in the on the DC side. And so that's pretty straightforward as far as modeling them. So here's what we've kind of covered so far. And before we close out, I wanted to see if there were any questions. By all means, as you have need to, okay, so there is a question, and actually it's the reason I wanted to bring up the 2-second rule. The question is, do these 2 seconds apply only for IEEE standard using arc flash options or also in IEC standards? I hesitate. So the answer is no, it only applies to IEEE. And it's an advisory comment in the verbiage of IEEE, and they make the addition that sound engineering judgment should be applied before 2-second rule is utilized in any circuit. And so that's why I'm reluctant to just automatically set any system up for 2 seconds. I think that covers everything I wanted to touch on. For sure, I encourage you to contact tech support if you have questions on utilizing EasyPower tools in any of the systems. Certainly, you can ask specific questions on the tools, or for any kind of library assistance, contact tech support at easypower.com via email or phone, and we will help you out. Thank you for attending today.